polymers, a universe of possibilities and headaches. These fascinating materials are the backbone of countless innovations and everyday items, but understanding their behavior. That's a challenge as mind-boggling as comprehending the vastness of space itself. The complexity of polymers can be overwhelming, with each tiny change in their structure leading to vastly different outcomes. You see, polymers are complex beasts. Their molecular structure can be manipulated in countless ways, leading to an array of different materials with unique properties. Their properties, like strength or flexibility, depend on countless factors: the length of the polymer chains, the types of monomers used, and the conditions under which they are synthesized, all play a crucial role. Think about it. The types of molecules in the chain, their arrangement, the forces between them, it's enough to make your head spin faster than a neutron star. Each interaction at the molecular level can have a significant impact on the material's overall behavior. Traditionally, scientists have relied on experiments to unravel these mysteries. They meticulously test different combinations and conditions to understand how polymers behave. It's a methodical process, but it's also incredibly slow and labor-intensive. But this approach is like exploring the cosmos with a horse and buggy: time-consuming, expensive, and limited in scope. We need a more efficient way to explore the vast possibilities that polymers offer. We need a faster, more powerful tool, something that can handle the complexity and vastness of polymer science with the precision and speed of modern technology. We need something that can sift through mountains of data, identify patterns, and predict the behavior of these cosmic polymers. Enter machine learning, a revolutionary approach that can transform our understanding of materials. Enter machine learning, the cosmic telescope of material science, with its ability to analyze vast data sets and uncover hidden patterns. Machine learning is poised to revolutionize the field of polymer science, opening up new possibilities and accelerating discoveries.
Breaking free from the lab. ML to the rescue. Machine learning, that powerful branch of artificial intelligence, is transforming the way we explore the universe of polymers. It's like having a supercharged assistant that can process and analyze data at lightning speed. Like a cosmic detective, ML algorithms can analyze vast datasets, identify hidden correlations, and predict polymer properties with remarkable accuracy. These algorithms sift through mountains of data, uncovering patterns that would take humans years to find. Imagine being able to predict the strength of a new plastic without ever having to synthesize it in the lab. This not only saves time but also resources, making the research process more efficient. ML makes this possible. By analyzing existing data on polymer structures and properties, ML algorithms can learn the complex relationships between them. This means we can forecast how a polymer will behave under different conditions before it's even created. This is like having a universal translator for polymers. It deciphers the language of materials, translating complex data into understandable insights. Instead of relying on trial and error, we can now use ML to design polymers with specific properties for specific applications. This targeted approach means we can create materials tailored to exact needs, whether it's for medical devices or aerospace components. Need a material that's both strong and flexible? Machine learning has got you covered. The possibilities are mind-blowing. Now we can design polymers that meet exact specifications, unlocking a whole new world of opportunities in material science. ML has the potential to revolutionize industries ranging from aerospace to medicine. In aerospace, it can lead to lighter, stronger materials that improve fuel efficiency. In medicine, it can result in biocompatible polymers for implants and prosthetics. It can accelerate the development of new materials, reduce waste, and drive innovation in ways we never thought possible. By optimizing the material design process, we can also make it more sustainable and eco-friendly. But how does it all work? What's the magic behind these powerful algorithms? Let's take a closer look at the ML algorithms that are powering this revolution. These algorithms use complex mathematical models to analyze data, learning from each piece of information to make better predictions and designs. Machine learning algorithms help computers learn from data and make predictions without needing detailed instructions. Supervised learning uses labeled data to predict outcomes, like guessing a polymer's strength, while unsupervised learning finds hidden patterns in data, such as grouping similar materials. Neural networks are great at spotting complex patterns and handling nonlinear problems, like predicting how composite materials behave. SVMs, support vector machines, are used to classify things, like whether a polymer can resist chemicals. Reinforcement learning teaches models through trial and error, making it useful for improving manufacturing processes. Principal component analysis simplifies large datasets to highlight the most important details. Choosing the right algorithm depends on the data you have and what you need to predict or solve. In conclusion, machine learning opens new doors in polymer science, enabling faster discoveries, smarter designs, and optimized processes, transforming how we develop materials for the future. Share your polymer challenges with us and we'll help find solutions. Got video ideas? Let us know and we might feature them. Thanks for watching. Don't forget to like, comment, and subscribe for more insights into the world of polymers.